Hey y'all, welcome back to chapter 11. We are going to start in section 3, perimeter and area of similar figures. And so we're going to combine what we have learned in the similar figures section in the past, and then what we have learned in this chapter. So starting off with the theorem 11.7, similar areas of polygons. So if two polygons are similar with the lengths of corresponding sides in the ratio AB, then the ratio of their areas is just A squared B squared. So we learned in the other chapters when we talked about similar figures, the side length of one polygon over the side length of the other polygon. And if we look at the example, we can say it would be A over B. And if you recall, this was called our scale factor in the other section, so we can still refer to it as that. We're just going to talk about it as a ratio, and that will also be the ratio when you look at both the polygons figures or perimeters. You can put the perimeters in the ratio and it will still be A to B. So this chapter we're going to really focus on the areas of the polygons. In this one, all you're going to do is square the ratio that you found above, and then we'll use that to find areas and other things like that. So let's go down to the first example. In the diagram, we know that triangle ABC is similar to DEF. We want to find the indicated ratios. So the ratio of the shaded to the unshaded. So shaded to the unshaded. Remember that DF, if you look in how it is labeled, DF is similar to AB. So we can say 9 over 6 is equal to, if you break it down, 3 over 2, and then the ratio would be 3 to 2. And now you want to, so by theorem 6.1, the ratio of its perimeters is 3 to 2, which if you notice would be the same as the side lengths. So the perimeter is the same. And now looking at theorem 11.7 from above, we're going to take that same ratio, but we're just going to square each value. So the area ratio will now be 9 to 4. And we can use that to find different things later on. So let's look at one more example. Your starting line should always be, what do you have in common between both? Do you have two of their perimeters? Do you have both of their areas? Or do you have corresponding side lengths? And that's what you're going to make your ratio with. So we want to find the area of A, B, and C, but first we need to find the area ratio. So I can say I have corresponding side lengths that are the same, so I'm going to make my ratio out of that 18 over 24, which I can reduce that down, and then I'm going to find the area of that. So let's reduce it down really quick. 18 divided by 24 becomes 3/4, and we can use that 3/4, so I'm going to say my small triangle over my little, or my small triangle over my big would be small triangle over my big area. So I would finish that by saying 4x is equal to 180, and then I would complete that by solving. Continuing on with our next example, we are buying two rectangular pieces of aluminum window screening. One is 15 feet long and costs $135. The other, similar in shape, is 20 feet long. The screen is sold by the square foot, and we know square feet tells us about our area. So what's the cost of the roll? So the ratio of the lengths of the longer roll to the shorter roll is, we have in common our side length, so we're going to use that. So longer is 20 to my shorter, which really gives me 4 to 3 as my ratio. So the ratio of the areas, remember, all you do is square that value. So you get 16 by 9. So this ratio is also the ratio of the screen's cost. So let's use that. So we would say our longer roll, 16 over 9, is equal to, I don't know what my cost is here, so let's call that X over 135, which they gave me. This is a proportion, so you just cross multiply and divide. So I would get 9x is equal to 135 times 16. Which would give me 2160. My x would be 240. So now I can say my cost of my longer roll is $240. We get to our checkpoints now. I have completed them. If you have any questions about the work, you can ask at a later time, but if you want to stop the video and work them out and check your answer, that would be a great idea. Moving on to example 3, we have 2 large billboards that are rectangular. The larger one is 12 feet high and 27 feet long, so let's go ahead and plug that in, 12 feet high and 27 feet long. The smaller billboard is similar, so we can use those ratios, to the larger billboard. The area of the smaller billboard is 144 square feet. Find the height of the smaller billboard, so we want to find our height. So right now, do we have anything in common? It doesn't look like it, but you can find something in common. Since we have the height and our base, we know that we can find the area of this larger billboard. So we could say 27 times 12 would give me an area of 324 feet squared for my larger billboard. Oh yeah, now we have 2 things in common, so we can do what? We can set our ratio up now. So using 11.7, the area ratio is a squared and b squared. So the lengths ratio would be a to b. So we need to kind of work backwards. The area would be 144 over 324, which reduces down to 4/9. So before we were going from the length to the area, now we're going in reverse, so we need to square root both sides, or top and bottom, to get our 2/3 ratio to find our lengths. If you have questions about that, remember a squared over b squared would be our area, and then to cancel those squareds, you square root to get a over b. And that's where that comes into play. Now we're going to use that. So any length of the smaller billboard is 2/3 of the corresponding lengths of the large billboard. So the height of the smaller billboard, I'm going to use my ratio times my side, and I would get 8 feet for the height. Now how would I use that to find my width? Well, I know that any length I can use my ratio that I found. Then I'm just going to multiply it by my longer side, 27 feet. So my width would be 18 feet of the billboard. So checkpoint number 3, you can go ahead and do, and then so pause the video, work it out, and then check your answer. Moving on to our last example. We have stop sign rugs that are regular octagons. Each side is 2 feet. So 2 feet. And the area is about 19.3 feet squared. You make a stop sign mat with the perimeter. So our perimeter over here is 72 inches. And since they're not in the same units, let's go ahead and put this perimeter in inches. So I'm going to multiply or divide it by 12, so I get 6 feet. So let's use that 6 feet for the perimeter. we want to find the area of the mat to the nearest tenth. So all regular octagons are of course similar, and that's what we want to get to so we can use our ratios. So the rug and mat are similar. Find the ratio of the lengths of the rug and mat by finding the ratio of the perimeters. Well, we don't have the perimeter of the top one, but we know that the perimeter is all of the sides added together. Since an octagon has 8 sides, I'm going to multiply one side by 8 to get my perimeter of 16 feet. So now I have something in common by both of them. I have their perimeters. So the perimeter of my rug is 16 feet. And they use 72 inches for my bottom rug, and we already converted it. So 16 feet over 6 feet, because I just divided it by 12. And I get a ratio of 8 to 3. Now I need to find my area. Let's fill in the blanks over here. Now I need to find my area ratio. So I will just remember square the top and the bottom. So my area ratio would be 64 over 9. So I'm just going to plug it in down here. 64 ratio over 9, which would give me to equal 19.3 feet squared over x squared feet squared. So I'm going to cross multiply again, and I would get 64x equals 173.7. So my area will be approximately 2.714 feet squared, and I want to get it to inches. So let's do our conversion. 2.714 feet. And I know there's 144 inches squared in 1 foot squared, so I would get 390.8 inches squared. So my area of my mat would be 390.8 square inches. And you can complete your last checkpoint. I hope this was good, and if you have any questions, please feel free to ask, and we will keep going with this chapter. Have a great day.